Okay, on to extremal graph theory. It's called extremal, but it's not extremal. It's very much mainstream graph theory. At least half of the best graph theory would call itself extremal graph theory. Sometimes people say the other half is structural graph theory. I mean, the use of the word structural is a bit bogus in mathematics. Everything is structural, but things can be more quantitative, numerical, or more building structures that are not numbers. Anyway, so that's very, very roughly how graph theory is organized into structural and extremal. We're not going to do very much extremal graph theory, and the classical basic result from extremal graph theory to Rahn's theorem will feature next lecture. And today I'll concentrate on something that is called sparse extremal graph theory. So extremal graph theory proper is dense, so it deals with classes of graphs or graph properties whose elements, whose graphs with those properties have the order of quadratically many edges in the number of vertices, like a complete graph, and sparse is anything that has only linearly many edges in the number of vertices, like trees or planar graphs. And of course that makes sense, not for individual graphs, never, but always for classes of graphs or properties. So there's sparse and dense extremal graph theory, and today will be sparse, next time will be dense, yeah. And real dense extremal graph theory involves something called the regularity lemma, and that will feature in graph theory too, and not in this course. Okay, let me start with Sophie's dream, Wagner's dream. What was Wagner's dream? Wagner wanted to prove the four-color theorem. At the time, 1935 was his thesis. It wasn't at all a theorem, it was a conjecture, but it was a famous conjecture. And his idea was to detopologize it, because it's so finicky and so sort of unpredictable and difficult to deal with graphs embedded in the plane, and to show that those need only four colors. How do you use the fact that they embed in the plane? Complicated, but we have one theorem, that's Kuratowski's theorem, that tells us something about graphs that don't embed in the plane, or even Euler's formula does. If a graph doesn't have, for example, a K5 minor, if a graph embeds in the plane, it can't have a K5 minor. So Wagner's idea to detopologize the four-color conjecture was prove that if G doesn't have a K5 minor, so for example, if G is planar, then it certainly doesn't have a K5 minor. Then you deduce from this assumption some structure, some structural assertion about G. If we're assuming not that it embeds in the plane, but we're assuming that it doesn't have a K5 minor, that might enable us to prove some assertions about what the graph looks like, some structure, and the hope was that this structure then enables us to prove that it only needs four colors. And there's no topology featuring in here, if this worked out nicely. So that was his idea. And he did prove something like that he did prove something like that, and we'll get to that in just a moment. And when he had done that, this prompted Hadwiger a mathematician in Switzerland to conjecture something inspired by this, or more precisely inspired by Wagner's theorem, that nearly implemented this, not quite, to prove more to conjecture more generally that for all R, so R would here be the 5, right, and that would be an R minus 1. That for all R, if you take a graph that doesn't have a KR minor, then it's enough to use R minus 1 colors to color it. Right? I mean, you can just conjecture that. So let me phrase it, if we phrase it like this, you never know whether this is R or that is R. So I want this to be R, so I'll invert it and say that if this is false, so if the chromatic is not at most R minus 1, but if the chromatic number is at least R, then G has a KR minor. So this smacks a bit of my earlier theme of finding a reason for a graph to have a large chromatic number, right? If you find a small, if you find a KR subgraph in it, then clearly it needs at least R colors. Now this doesn't quite work like that because even if you find a KR minor, that doesn't mean that the graph must have large chromatic number. So the converse of this is definitely not true. You can have KR minors with low chromatic number. Think of an example. Think of our favorite graph of low chromatic number that is dense in every other respect, or KNN. Right? So, yeah, so the converse is not going to be true, but this is something one can wish for. And for some reason, this has become perhaps the most famous conjecture in graph theory. Don't quite know why. Nobody knows any good reasons of why that should be true. And I think most of the experts think it's probably false, or if it is true, then it's sort of true by fluke, because, I don't know, there are certainly many graphs that satisfy that. One can prove in some sense that almost all graphs, that's a probabilistic statement, satisfy Hadwiger's conjecture, but that hinges more on the notion of almost all than on Hadwiger's conjecture, so that's not a difficult theorem. Right, but anyway, so that's a famous conjecture inspired by this program that Wagner set himself. And let's just check some small values of R here. So what happens if R is 2? If a graph needs at least 2 colors, then it contains an edge. That's plausible. How about 3? If a graph needs at least 3 colors, then it has a K3 minor. That's the same as having a K3 topological minor, because the max degree of a triangle is 2. So when does a graph have a topological K3 minor? If and only if it has a cycle, contains a cycle. So we want to show that if our graph needs 3 colors or more, it contains a cycle. Yes, it does, because if it doesn't contain a cycle, it's a forest, and we can 2-color forests. Okay, so for R equals 1 to 3, that's true. R equals 4, that's still true, but that's a non-trivial theorem, so that's very nice. And that was proved by Wagner in his thesis. That's true for R equals 4. And Wagner proved this using his approach. So he showed that if a graph doesn't have a K4 minor, and it has a certain structure. And from that structure, we can read off that three colors are enough. So what does Wagner prove? So that's theorem 731. Oh, well, this can't be right. I'm a little confused. So about the timing. So anyway, a paper 731 Wagner. It says 1960 in the book. And he proved the following, that take any graph G, if G is edge maximal, without a K4 minor, such that G doesn't have a K4 minor. So G doesn't have a K4 minor, and if you add an edge, not a vertex, just an edge, then it will have a K4 minor. Then G looks like this. I'm not going to give you the full statement. The full statement's in the book. I'll tell you what these G's look like. There are two ways of telling you. One is to say you start with a triangle, then recursively add triangles, pasting them onto what you have already along an edge. So we take another triangle and paste on this edge, so we get this. Then maybe paste onto this edge another triangle, maybe use that edge again to paste yet another triangle on there, and yet another triangle on there, and then maybe on this one, and on that one, and again on this one, and so on. Right, recursively start with a triangle, and then when you've constructed something, pick an edge, take a triangle out of thin air, and paste it along this graph that you have already, identifying an edge of that triangle with this chosen edge. That's a class of graphs, and all the edge maximal graphs without a K4 minor look like this. There's another way of defining that class, and that says recursively triangles are in the class. Now take any graph in the class, find an edge. Take any other graph that is in the class, so one that has also been previously constructed, find an edge, and identify those two edges. Right, so this is slightly more general, this construction method, than what I told you there. What I told you there was that this is always a triangle. If you allow two general graphs that have been previously constructed, you can't generate more than what you can generate here. That's a little exercise, it's not hard. Right? Just to show you that two things, there are two ways of constructing that class. So here, you'd get this graph with two constructed with two vertices that are adjacent and along which we identified. Right. Now, why does that prove Hadwiger's conjecture for 4? Well, we need to show that all these graphs can be colored with at most 3 colors. Right, so if you follow this approach, well, why is that enough? Because if we have any graph without a K4 minor, make it edge maximal without a K4 minor, for good measure. Just throw in edges until it is edge maximal, then color that. And if that can be colored with at most 3 colors, then so can your graph. Right, so there's no loss of generality in assuming that the graph is edge maximal without a K4 minor. So if we follow this construction method, then it's easy to see by induction along the construction method that the graphs can be colored with 3 colors. Suppose you have already colored something in that class, and now you add one triangle along an edge. These 2 vertices will have some colors, and you want to make a new vertex adjacent to those 2 and give that vertex the 3rd color. All right, so that's easy. This is also easy and worth remembering, and that is more generally, if you, let me draw a new picture. So if you have 2 graphs, each of them can be colored with K colors, and they overlap in any complete graph. One, a K2 or a K17 if the little k is bigger, right? Then this whole thing can be colored with at most K colors. And why is that? Well, you just color the left graph. Then you go for a walk, and you come back and you color the right graph. Now you find that maybe these 2 colorings are not compatible because on the intersection you've used different sets of colors. But never mind, you just take the second coloring and you permute the colors. You just rename them so that the colors used on the intersection are precisely those in the first coloring, and then they fit together. Right? So that's a nice, very simple, but a nice little fact to remember in graph coloring. Okay, so I'm not going to prove that theorem. I think it's a proposition even, is it? No, it's a theorem. I'm not going to prove that to you. The proof is not hard. Sort of case analysis. You can read it in the book. Don't have to learn it. It's easy. But it's important to remember the assertion. And there's a cute little corollary. 732. Every such G, that's edge maximal without a K4 minor, has exactly 2 mod G minus 3 edges. In particular, they all have the same number of edges. And that's quite remarkable. All maximally planar graphs have the same number of edges, but normally just from the assumption that they're both edge maximal without this, they could be sort of edge maximal in sorts of different sorts of ways, where you get stuck and you can't add another edge without creating a K4 minor. But in fact, that doesn't happen, well, it happens in different ways, but it always happens at the same number of edges. And that's because these edge maxima graphs without a K4 minor look like this, right? So you just check this formula for a single triangle. So twice 3 minus 3 is once 3. And a triangle does have once 3 edges. So bingo. And then by induction, well, you add 1 vertex and 2 edges, right? So you maintain this in the induction. When the number of vertices rises by 1, the number of edges rises by 2, and never mind the constant. So that immediately gives this formula, and this one does too. You just work out the numbers, and that's that. So that's a cute little corollary, cute little fact to remember. Yeah. And now, back to Wagner's dream. Wagner did prove a theorem about R equals 5, and that's 634, 734. And I think that is already in his thesis, so the other one must be in his thesis too. Maybe he only published it in paper form in 1960, I don't know. So certainly Hadwiger's conjecture didn't exist at that time because he fashioned his conjecture after Wagner's theorem, after that theorem. So Hadwiger made his conjecture in the 1940s, 45, 47, something like that. Okay, so what did Wagner prove for R equals 5? The edge maximal, same as here, graphs without a K5 minor can be constructed recursively from, that means starting with, maximally planar graphs okay. And a particular graph, W for Wagner, by pasting, identifying, like here, along K2s and K3s. If I remember correctly, you can even start from 4 connected maximally planar graphs and use triangles to paste along only when those are involved, but only those are involved. But as soon as you have a W involved, that doesn't contain triangles, so you need to use a K2. And what is W? 1, 2, 3, 4, 5, 6, 7, 8, and all the diagonals. So 8 vertices, and then you draw an 8 cycle and then an edge joining any pair of opposite vertices. That's W. There are other ways of drawing it. One is like a bipartite graph with the bipartitions. I'm not going to do that for you, but I'll show you a different interesting drawing. So our 8 vertices start life as a ladder, like this, and then you you join these two K2s at the end, but with a twist, so like a Mobius strip. That's called a Mobius ladder. That's the same graph as that. Okay, so this is W, and that's his theorem. So, what about his dream? Well, we have a structure theorem for graphs without a K5 minor. And it says, take some ingredients and then paste along complete graphs. That's fine, that preserves the chromatic number, that doesn't push it up, these identifications. So all we need to do is show that the ingredients have chromatic number at most 4. What are the ingredients? Well, it's this graph here. Yeah, that has chromatic number at most 4, easily, I think, 3. So what are the other ingredients? And unfortunately, the other ingredients are the maximal plane graphs, or planar graphs. So here comes the 4-color problem raising its ugly head and grinning at Wagner's attempt. So you need the 4-color conjecture or theorem in order to color the ingredients, and then you can lift everything. So what Wagner in fact proved is that Hadwiger's conjecture for 5, which of course comes later than his theorem, follows from the 4-color theorem, which comes even later. And at the time, it was known as, well, at the time after Hadwiger, this theorem was known as Wagner's equivalence theorem. Maybe you can find a reference to that still these days somewhere. Okay, so Wagner's dream is shattered in pieces, but it's a very nice structure theorem, and it had enormous repercussions, and it inspired all of graph minor theory. So graph minors is chapter 12. It's a very, very profound and beautiful part of structural graph theory, and it all goes back to Wagner's theorem here. The idea is to describe the structure of graphs that don't have a particular minor, as in this case K5, but it works for other minors too, by showing that they can be pasted along in this sort of tree-like way from ingredients that can be structurally described, like the maximally planar graphs. So that's graph minor theory. Comes to graph theory 2. All goes back to this very influential idea and first theorem of Wagner's. Questions? No. Okay. Then let's see what we can do to approximate Hadwiger's conjecture if we can't prove it. Maybe I ought to say that Hadwiger's conjecture was in fact proved for, well, R equals 5 by way of proving the 4-color theorem. I've told you about that. And essentially the same authors proved Hadwiger's conjecture for R equals 6 as well. That's a tour de force in case analysis, and it's a fantastic achievement and a horrible paper. But it was a big thing at the time. And there's no hope really to follow that same approach or a similar approach for bigger R. Right. So, 7.2, this was 7.3. 7.1 will come next time on Thursday, and 7.2 now is forcing minors. So we're trying to force the existence of a minor we wish for, like a KR, by making some assumptions, such as the graph has a large chromatic number. So if the chromatic number is large, can we deduce that there's a KR minor for large R, right? Where this large may be a lot smaller than that large. So the idea is very, very roughly, as a first approach, if we wish for a KR minor, will a graph contain it if we assume that its chromatic number is big enough as a function of R? Right, so is there an end-to-end function such that for all R and for graphs G, if the chromatic number of G is bigger than f of R, then G has a KR minor, right? That's just this spelt out. Yes, there is such a function. So let's find some good slow graying functions that do that. But before we worry about growth, let's prove that such an f exists at all. So we would like to show that we can find a KR minor, and we'll try by induction on R if the chromatic number is large enough. Okay, so how could the induction step work? Well, so idea, induction on R. Well, we might try to show that if the chromatic number is large enough, then there exists a vertex whose neighborhood spans a subgraph that has large enough chromatic number to have a KR minus 1 minor. Right? That would certainly make this induction work, because we could then add this one vertex to its neighborhood, and it sees certain branch sets, and yeah, it sees all of them. So we get a KR minor. So the question is, suppose we have found f of R minus 1 already. We have some value of chi of the chromatic number that ensures that a graph has a KR minus 1 minor. Can we find a value for f of R? So a value for the chromatic number that ensures that there exists a vertex whose neighborhood has chromatic number at least f of r minus 1. Okay. Before you tell me that this is obviously flawed, which I fear you might tell me in just a few seconds, try not to see why it's flawed, but why it's suspicious. If this proof approach worked, something much stronger would work as well. You see that? I want to sort of make you sensitive to the prospect that there's something fishy about this, because the prospect is that we'd prove something much, much stronger if that approach worked. You see that? So what are we doing in the induction step? We're just adding one vertex. Well, a suitable vertex, but still only one vertex. And we're assuming that there's a kr minus 1 minor in there, and then we just make a kr minor out of that. That's not any old kr minor. It's a very special one. It has a branch set of size 1. But then, why not prove that all graphs, if the chromatic number is large enough in terms of r as a function of r, have a kr minor, all whose branch sets are of size 1, or maybe all but the first or something. And we'd be proving that they all have a kr minor, kr subgraph. And that's clearly not true. Right? So, well, is it true? That's something we discussed before. Does every highly chromatic graph contain a large complete subgraph? And the answer is no, by Erdős' theorem, if anything, if nothing else. So there are graphs of large chromatic number as large as you like. So for example, f of r, whatever that might be. And girth also as large as you like, for example, that large or even bigger, certainly bigger than r, that have chromatic number, that large chromatic number and that large girth. So this would fail dramatically because as soon as the graph doesn't have a triangle, right, girth not bigger than 3, there would be no edge in here. Right? And Erdős' theorem also shoots down the more sensible approach than this, picking one vertex, even a suitable vertex, and hoping it has a neighborhood of large chromatic number is stupid because it's so suspicious. But even if we say, okay, let's hope for something like this, a vertex that's at the center of some branch set, so that contracting this entire branch set gives you a kr. That would be less suspicious than this, because we'd be getting krs with big branch sets. Okay, of a particular structure, but never mind. But that too is sort of basically flawed. Why? Well, as long as the diameter of this, or the radius of this, is bounded, so this would be the ball around a vertex V of radius n. So all vertices of distance at most n from some particular vertex V, if we take that as a branch set, can we hope that we find such a thing for fixed n, such that this has large chromatic number? And the answer is exactly the same as before? No, we can't as long as n is fixed, because any such edge here would create a cycle of length at most 2n plus 1 or something, or 3. Right? And the whole graph might have large chromatic number without containing a cycle that short. Okay, so that doesn't work either. Next attempt, or next question, if we don't fix n, right, this counter-argument depended on n being fixed, and then we said, well, whatever n is, even if it's 1,000,000, we can find a graph of girth bigger than 1,000,000 plus 3, or 2,000,000 plus 3, and chromatic number also that big where this doesn't work. What if we let n be variable? So can it happen that when we how do I do this? Draw the distance classes. Around a vertex, and we allow ourselves to contract. Which color would you like for contract? Blue? To contract some such ball. But I'm not saying which one. I'm not fixing the n. Might that work? So can it happen that for every such ball, the neighborhood has low chromatic number, but the whole graph has as large chromatic number as you like? And there's a very simple observation that says no. So if these neighborhoods here so, all right, the vertices at distance, I don't know, n, and there's some edges between those vertices. That's the graph Gn. Right, all the vertices at distance n from some fixed vertex, and what they induce. If all these have small chromatic number, then so does G. How small? Well, if all these Gn have chromatic number as most k, how can you color G? With how many colors? Maybe a few more than k, but you see that? No? Well, first observation, we can use the same color set of k colors for alternate Gn's. So if we color Gn and Gn plus 2, we can give them the same k colors because there's no edge between them. Right? So every distance class sends edges to the previous distance class and to the next distance class, but that's all. You can't have edges between two distance classes that are 2 apart or more, because that edge would make this distance class or that particular vertex closer than in its distance class. So these Gn's have no edges between them when you just consider all even n, or when you consider all odd n. So for all even n, we can use the same set of k colors. For all odd n, we can use the same set of k colors. So here we have k colors, and here we have k colors. And then we have used 2k colors altogether, and we can color all of G. Right? So in the induction step from R minus 1 to R, we have to increase the number of colors that we allow ourselves by a factor of 2. But only that. So that's a theorem, also Wagner, 1964. For all R and for all G, if the chromatic number of G is at least 2 to the R, then G has a KR minor. Proof by induction on R. Right? So if G has at least 2 to the R, needs at least 2 to the R colors, then one of the Gn must use at least, or need at least 2 to the R-1 colors, because if they all needed fewer, then twice the maximum would be less than 2 to the R, but would suffice as colors for G. So if G needs 2 to the R colors, there exists a Gn that needs 2 to the R-1 colors, and then that by induction will have a K R-1 color, complete minor. Right? So use that complete minor in that Gn and contract everything inside to one vertex to get a KR minor. So that's that. So this isn't explicitly in the book. This is an exercise. So if you'd like to sort of take a photograph of this or whatever to remind yourselves of the proof is easy. But I should have told you that before. But I would like that to be part of the course because it's such a pretty thing. If you go home and you can't remember the proof, do ask, right, in the exercise class. Okay. So, next attempt is also an interesting idea, a bit like Wagner's dream. I don't know whether it's anybody else's dream, but the chromatic number is such a mysterious invariant, and we don't understand it. So maybe it's easier to prove by induction something stronger. And the something stronger would be that we get a KR minor, assuming less, not that the chromatic number is big, but that something else is big that would follow from the chromatic number being big. For example, the average degree. Right? So if your chromatic number is at least k, then you have a subgraph of min degree at least k minus 1, and so that has average degree certainly at least k minus 1. If the chromatic number is large, then the average degree is certainly large, but maybe that suffices to prove that you can find a KR minor. So that's an interesting roundabout way of trying to prove something like Hadwiger or an approximation to Hadwiger's conjecture. And so Marder 1967 proved the first such theorem. I think there might have been a Harlin theorem just before that with a slightly worse bound, but Marder's theorem was that if the average degree is at least 2 to the r minus 2, so that's a much weaker assumption. Not only is 2r minus 2 a little smaller than 2 to the r, but it's also assuming not that the chromatic number is that large, but only that the average degree is that large, then we have a KR minor. Okay, so let me prove that. That is in the box, so you don't need to take notes there. And the idea is the usual one. Since we're after a minor, we may as well try to contract things to get some more assertions about the graph that we have. If we contract it maximally, so that blah, then at least we know the assertion about the graph we obtain, that if we contract anything else, anything further, then blah will fail. So whatever blah is, it'll be some information. Now, what's a good choice for blah? Well, the asset that we have. Right? So we're assuming that the average degree is at least something. So let's contract as much as we can, maintaining that. We're not losing anything, because the graph that we're getting to might as well have been our original graph, because it satisfies that. So any graph satisfying that will have to have a KR minor. So we're not losing anything. Let's do that. So I want to call that, no, it doesn't get a name. Let H be a minor of G with average degree at least 2 to the r minus 2. And let me write it differently. Let me write it in terms of epsilon, which is the same thing. It's just half d. So that's epsilon is at least 2 to the r minus 3. Yeah. Let's consider this minor of G, and let's find a KR minor in there, and then obviously G has one because H is a minor of G. So pick a vertex X, and let H be the neighbors of of X. Right, so here's our vertex X. And it has a certain neighborhood. Right, what can we say about this H prime, this neighborhood? Well, quite a bit. The min degree of H prime is big. What is it? It's at least this, 2 to the r minus 3. And why is that? Well, if we had a vertex of smaller degree, then we could say y. Then we could contract the edge xy, and we'd be losing one vertex, and how many edges? Well, fewer than 2 to the r minus 3, one fewer at least, plus this edge. So we're losing at one vertex and at most 2 to the r minus 3 edges. Now remember proposition, I don't know, the first lecture, second lecture, when we found a graph of a large min degree assuming large average degree, we lost a factor of 2. Right? If we contract this edge, we're losing one vertex, and at most this many edges, so the epsilon is not going to go down. We're not losing enough edges to make it go down. So if we could do that, then that would contradict the minimality of H. Okay, so that's, this will be the case. The min degree is at least 2 to the r minus 3. And of course, the average degree is no smaller than the min degree. It's also at least 2 to the r minus 3. But that is just the value from the theorem for r minus 1. So the average degree of H prime is at least this for r minus 1. So by induction, H prime has a k r minus 1 minor. So that has a k r minus 1 minor, so G has a k r minor, and we're done. Right? So H has a k r minor, and since H does, G does. And there's nothing suspicious about this being just one vertex, because it really is a branch set in G. We contract it already. Yeah, okay, questions? No. Okay. Then I'll have a final theorem for you. I'll put that here. Right. And that is also Marder 67. Oh, are both 67? It says so, okay. So that's Wolfgang Marder. He used to have the chair in Hanover, and he just died in January. And he proved that if the average degree of G is at least something I'll fill in a moment, then G has a KR topological minor, so it contains a TKR. That's a stronger assertion than having a KR minor, substantially stronger. You need these vertices of large degree in there, for example. And the bound he needs is 2 to the R choose 2. So, of course, for all R and for all G. Okay. And the proof is fashioned on the same theme as that one. So we also contract as much as we can, and then maintaining our, our assets, which is this, and then, well, find a KR minus 1 topological minor in what we have, and how can we make a KR minor in the whole graph? Not really. So the induction is slightly cleverer than that. It's not on R. It's on a smaller, more detailed parameter. So we'll prove by induction on M, and M is between R and R choose 2. The following, we'll choose the following, that if the average degree of G is at least 2 to the M, so we want to end up with this. That's the final step in the induction. So if the average degree is at least 2 to the M, that should give us our result. Then there's a TX in G with R vertices and M edges. Right? So we always want R vertices. We want a TX. At the end of the day, that should be our TKR. When is X a KR? Well, if it has R vertices and M equals R choose 2 edges. Right, we'll certainly get what we want at the final step of the induction. The start of the induction I'll get to in a moment. That's easy but not trivial. And then the induction step will do what? Well, we'll have some branch vertices already by induction. In the induction hypothesis, we'll get an X prime subdivided, which already has R branch vertices and enough subdivided edges to make M-1 edges on those fixed R vertices. And we'll just need to find one more edge. And we'll be finding that one more edge subdivided as a path through something we'll contract. Right? Like this X here. So let's just do the induction start. Why do we start the induction at R rather than 1? Well, because we need enough vertices. Right? We need R vertices to have it. And the vertices will remain fixed. We'll just be adding edges. So what do we need for M equals R? We want an X of R edges and R vertices and R edges. You think of any graphs that have the same number of edges as vertices? Yes, you can. Cycles. Right? So all we need is an X that's a cycle, and we need a TX. So that's all we need. We don't need an exact R cycle, but we need a cycle that has length at least R. Then it's going to be a TCR. Right? Okay, so what assumptions will give us a cycle of length at least R. Well, if something, then G has a cycle of length at least R. You remember, also first chapter. We're in the business of average degrees here. Right? Can you think of a degree condition that gives us long cycles? Yes. If the min degree of G is at least R minus 1. Remember, that was take the longest path, and then if the last vertex has degree at least R minus 1, all its neighbors have to lie on that path, otherwise it wouldn't be maximal. So if you have at least R minus 1 neighbors, the last edge is 1, and then you have others, then all in all you have an R cycle, at least. Okay, so that's enough. Well, we don't have any min degree assumption, but only an average degree assumption, but that's easy. That's also proposition, I don't know, 1 to 2 or something. So it's enough to have average degree at least twice that. Right, then we find inside this graph of average degree at least twice that, we find one of min degree at least that. And all we need now is that what we actually have, that the average degree is at least 2 to the what do we have? The average degree is 2 to the m, so that's 2 to the r, right? And we need twice r minus 1. So we need that 2 to the r is at least 2r minus 2. And if r is at least, I don't know, 2 or something, then that's correct, or 1. Right? Okay, so that's the induction start. Induction step same as before, contract as much as you can. It's enough to contract one set really vigorously. So let U be a set of vertices connected in G, and let it be maximal such that when we contract it, then we still have the average degree, what we're assuming we have, is at least 2 to the m. Right? We can certainly do that. So this is our U. Okay. Let's look at the neighbors of this set U. Right, this is a connected set. Look at the vertices that have send at least one edge to this big set. Then consider the graph H, that is induced by these neighbors. So this is H, and the min degree of H, as before, is what we used to have. So min degree of H is at least 2 to the m. Right, why? 2 to the m minus 1. The epsilon that we're assuming is at least half the average degree, is the average degree. So the epsilon that we're assuming is at least 2 to the m minus 1. So the min degree must be at least 2 to the m minus 1. Every vertex has at least that epsilon many edges going to other vertices of H, because if it had fewer, then together with this, that would be at most epsilon, many edges, and then we could contract this vertex, increasing u, so incorporate that into u, and maintaining the epsilon that we have, or equivalently maintaining the average degree that we have. Okay. So, by assumption, by the induction hypothesis, there's a Tx in H with R vertices in X, so X has R vertices, and 2 to the m minus 1 edges. M minus 1 edges. Right? So that's the induction statement here. There's an X, there's a Tx with R vertices and m minus 1 edges. Right. Let xy be a non-edge. I shouldn't write that. So be non-adjacent. In X. So pick 2 of these branch vertices that doesn't have a subdivided edge between them in H. Right? There is such a pair because we have R vertices. Otherwise, that would be complete already, but it can't be complete because we only have m minus 1 edges. Right. And then, from one of these and the other of these, go to U, and since U is connected, find a path. Okay, so add xy path through U to turn tx into t x plus xy. And that's what we want. Okay, end of the induction. So, yeah. Questions? No. Okay, in that case, I'll just give you an overview now. Best possible results on forcing KR minors or topological minors by assuming large average degree. Okay, so what about forcing topological complete minors? And that's 7, 2, 3. There's a constant C, universal constant, just a number, such that for all R and all G, if the average degree of G is at least this constant times R squared. So R squared is a little smaller than 2 to the R choose 2, right? That's very nice there. Then G, okay, let me write it. In subgraph notation, then we have a TKR. Right, so, yes. Thank you. Yeah. Thank you. Any other nonsense? You tell me later when the microphone is switched off. Right. So, yeah, so what is C? C is a handful. It's like, I don't know, 4 or 5 or something. In fact, it's a very small constant, and this constant was almost optimally determined by Paul Wallen, Kenichi Karawabayashi, and 3 of you. 3 Hamburg students, Jan Oliver Fröhlich, Julian Pott, and Theo Müller. It's a few years ago, unfortunately, since this still isn't written up properly. You can read versions in various theses and habilitation theses and so on. No, not habilitation, just theses. Of those 3 students. But Paul Wallen is going to write up the whole thing, and he wants to get a really perfect paper out of this, and therefore it's been lying in his drawer for some 5 years or 10 or something. So this is still not published, but that's the best possible, well, I think up to one best possible constant C. Okay. But even the existence of such a C, that was the big breakthrough, or the first big breakthrough. There are various authors that proved that independently, and you can look up the names in the end of chapter notes. Then there's theorem 7 to 1 or 2 probably, I think it's earlier. No, it isn't. 4. Oops. Same thing. There's a constant C such that for all R and all G, if the average degree is at least, and now we only want not a topological KR minor, but just a KR minor, and then we can make do with a smaller function of R. So that's at least R root log R. Then G has a KR minor. And that was proved independently in the 1980s by Sasha Kostochka, and a few years later, but independently by Andrew Thomason. And Andrew Thomason also determined this number, I don't know, up to, 10 digits behind the decimal points or something like that. So that is known. And interestingly, this theorem shows, this theorem is best possible. You can't get rid of this root log R factor. The growth rate of this function is the right one. So smaller average degree than this will not force a KR minor. And one proves that with using random graphs. And this means that this roundabout way of maybe proving Hadwiger is doomed, right? In Hadwiger, we want an average degree that comes from the chromatic number being at least R. So the average degree is, I don't know, the min degree is R minus 1 or something. Even 10R or 100R is not going to do. So that's an interesting, so the converse of this theorem here, that one does need the average degree to be of this order to be sure that we get a KR minor. That shatters the dream of proving Hadwiger by way of showing an average degree argument rather than using the full strength of the chromatic number. And we're back to the mysteriousness of the chromatic number as an explanation of why we haven't disproved Hadwiger.